All right, let's get back to the problem. This is assignment 4, and here the job is to implement a append vector. We're going to append the elements from W onto V. Notice that W is declared as const because it's read-only. V is not declared as const because the function is going to modify V. So the basic operation is going to be to range across the elements of W and append each one individually onto V. So that means we need a loop. And it's a for loop because we will know exactly how many elements to add on. We start at 0, and as long as I is less than W.size, I will increment I. And then push back W of I. That's the solution for that one. Any questions on that? And notice that there's no return statement because we're not returning a value that's declared as returning void. We'll need that actually. This whole thing should be, on the quiz you can just put that. That's fine. Or the assignment you can just declare it like that. That's fine. But I just have it written out like this. All right, let's look at the next one. Count occurrences. So here we have a vector V, and we want and an integer k, and we want to count how many times k appears in V. And V is also declared as const here because we only need read-only access to V. K, we don't declare K as const. We're not modifying K, but still we don't declare it as const because const is only applies to references. And actually, I think we could declare that as const. I'm not sure. It doesn't seem to be important though, because we're going to operate. K will come in as a copy. Because I'm getting off on a tangent here, I don't want to go in that direction. But we will essentially get a copy for K, so there's no need to declare it const. Let's implement this. Count the occurrences of K and V. Well, that's a problem we need to count. So let's start a variable for counting, and we'll call it sum. And we'll start with 0. So we haven't seen a K yet. Now let's iterate through across the indices for V. So for each I, let's check V of I. If V of I is K, then let's go ahead and increment the sum. Actually, I don't like sum. We're not adding them. Let's call it count. I'm going to change that to count. Sum sounds like we're adding the values together. So count is a better name. What's that? You know what? My hearing is really weak. And hold on one second. We need to return that, by the way. Yeah. Count is a better name. Sum sounds like we're adding the values together. But we're not. We're just counting the occurrences. So count. It's just a better name. Any questions on that one? How about this one? Is strictly increasing. So V is a vector of integers, And we need to return a bool, true or false. Does V contain values, does it contain integers which are strictly increasing? If it does, return true. If it doesn't, return false. All right, to make this determination, we need to look at pairs of values in V. So we need to range through V. So let's just start. We know we're going to need to range through V and examine what's inside V. So just as a beginning, we're going to write a loop. This is an approximate solution. I think we're going to probably need to make an adjustment. I know that we're ranging through V. We have to confirm something. We have to confirm that each value is bigger than the value before it and smaller than the value after it. So we could start at 0 and end at a v dot size minus 2, or we could start at 1 and end at v dot size minus 1. I'll start at 0. And I'm going to compare v of I with v of I plus 1. So if v of I let's suppose that for some I, we find that, that v at slot I is bigger than or equal to the value at slot I plus 1, the next slot. So that means it's not strictly increasing. We found a pair of values that that violates the criterion that the sequence is strictly increasing. So we know at that point that that we can return false. Sorry about that. We can return false at this point because there's no need to look at any other pair of values. See, every pair of values has to satisfy that condition in order for the function to return true. So if we get to this point in the code, we know that we looked at every pair of values, so we can return true. Now I used v dot size minus 1 here because I don't want I to hit the last valid index. Because if I reaches the last valid index, I plus 1 would be an invalid index, and that would be a runtime error. So I need to let I approach that last valid index, but not reach it. Just stop at one value, one slot less than the last slot in the vector. Is everyone clear about that? Any questions on this one? This is it. Okay. You know, I can explain it to you, but you really do need to think it through on your own. And it also helps to code things up and do tests, of course. Let's look at number 4. This is the function is all zeros. This function takes an array of rows and columns, right? A two-dimensional array. And rows is a constant defined here, and columns is a constant as well. So what I want for the code is for you to use the variables rows and columns. So we don't know what these values are. They're defined in the program somewhere, and that when this function runs, then rows and columns are summed out. All right, so here it's also similar to the previous exercise. The function will return true if all of the elements in the two-dimensional array are zeros. So we need to look at every element. If we find one that's not zero, we return false. If we look at every element and we don't return false, then we return true. So let's go ahead and do that. We'll use indices I and j because we need to range across rows and columns. If we find a non-zero value, we return false. So these two loops here, they set I and j to every valid pair of indices into this two-dimensional array. I ranges across the row indices and j ranges across the column indices. So this is called a nested loop. And once again, the algorithm is to look at each element of A of ij, and see if it's not zero. If it's not zero, then let's return false. Here I'm using a form of this if statement that I don't usually use in this class. Here I've got the if statement, with a block of statements with just a single statement. So I could have used the same form here as well. So if there's only one statement that's comprises the body of the if statement, then you can omit the braces. Oh, there's something missing. We need to return true, exactly. So if we look at every value and we don't find something that's not zero, it means we looked at everything and everything was zero, so we can return true. All right, it's some confusion about binary search. On my last presentation about binary search, I implemented a function that returns an integer value, which is the index of some value k in a vector v. But on the assignment, I asked you to implement a function called contains that searches through v using binary search and returns true or false based on whether it found the value or not. If it finds the value, it returns true. So I want to show both those solutions. And also want to I want to type it up now, not so that it runs on the computer, not so that it compiles and runs, just so that what I'm going to write down is I'll call pseudocode. And that's it's not real code. It doesn't compile, but it expresses the algorithm in human form, so that humans can understand it, but computers cannot. So here's a binary search, and here's the function we're going to, we'll call it, say, function binary search. I'll take a vector v and a value k. Find k in v. Return. I'll do it like this. Return the index of k in v. If found, otherwise return -1. That's the function. So let's do it like this. Let's declare some variables here. So we're going to have we have the what is it? Start. We say start is 0, and the end is v. I'll do it like this: size of v -1. Or I could say the last valid index of v. This is the last index in v. Say valid if we like. So that starts the algorithm off. Then we have a loop. While the start index is less than or equal to the end index. Now here, in class last time, I didn't think about binary search before I came into class. I just solved the problem from scratch, just in that moment. But then in lab, I was talking to one of the students. I don't remember your name, and we worked through a better solution to binary search. So I remember that solution now. So I'm going to present what I think is a cleaner sort of expression of the algorithm. Although what I presented in lecture last time works, and we thoroughly tested it. So in this alternative solution, which is just a little bit off, it's like kind of like one off, one index different from our other solution. It's essentially the same solution. We are comparing S with E, but we're going to continue the loop. If S and E are equal to each other, we're going to continue to process the body of the loop. It's only when S gets larger than V that we stop. So the first thing we do inside this loop is to compute a middle index. So let's go ahead and take the average of S and V. That gives us the index which is in the middle of S and E. And then we're going to check to see that if V of M is the K that we're looking for, then we'll return M. Sorry. So we calculate the midpoint, the middle index. Look at the value there. If it's the value we're looking for, return that index, M. So if it's not there, then we're going to move start up to M plus 1 or E down to M minus 1. So we need to compare V of M with K. Let's suppose it's less than K. So we know that V of M is not equal to K at this point in the code. So let's, and I don't want to mix notation here. I'm using another notation just to show you that with pseudocode you want to be consistent, but It doesn't have to be. It doesn't have to look like the language that you're working in. Right, so this pseudocode could work for any language. So let's suppose that the value at m is less than k. That means the value at the midpoint is big relative to k. So we want to slide the n index down to m minus 1. We don't need to set e to m because we know that at m, k isn't there. So let's set it to m. But let's suppose that v of m is bigger than k, which has to be the case if that previous condition is false. Then we're going to slide s up. We don't need to set s to m because we know that the value at m is too small. So let's set s to 1 just beyond m. That way, if s, then m is s and e, and here that e will be set to a value smaller than s, and here s will be set to a value larger than e. That will terminate the loop when, in the last pass, when s and e are equal to each other.
Is that supposed to be backwards? If k is bigger than the midpoint and turning the beginning forward?
Let me think for a sec here. So if k is bigger than the midpoint, then we want to bring the start up. That's right. So if k is small, then relative to what's at m, then we want to bring e down. That's right. Thank you. Does everyone see that? Okay. Thanks for that correction. So if we complete this loop and we don't, if we exit the loop, it means s has become bigger than e, and we've tried, we haven't found it, so we'll return minus 1 at that point. And look, the indentation is important. This is the same level as the while loop. That shows, this indentation I have here is precise. This shows that the return is executed after the while loop completes. You might want to play it safe. Make sure that I know that you know that, and put braces in there. This is playing it safe. Now you don't have to worry about your indentation being visually accurate. You're showing me with braces that return minus 1 comes after the body of the loop. All right, let's take a look at the other formulation of the problem. So here it's we want to return true if k is in V. Otherwise, return false. And maybe we call the function something like contains. I think in the assignment I call it contains, right? And then that returns a Boolean value. So we do the same thing. We just at this point, we found it here, so we just return true, and here we didn't find it, so we return false. instead of returning the index, we return true or false. So that covers binary search and also assignment 4. We looked at assignment 3 solutions previously as well. So is there? I mean, that's pretty much it at this point as preparation for the quiz. There's one more topic that we need to cover, and that is sort. Sorting so if you have a vector of values and they're out of order, how do you put them in order? That's called sorting. And we could do that now. We have time to start that now. If you want to start that, we could start that now, or else we could continue to talk about preparing for quiz 3. What do people want to do? So one more topic to do. It's sorting. So if we don't do it today, then we'll need to do it on a week from today, which is our last meeting. Any preference? Want to wait till meet when? What? Final review? We'll have to do that on Monday as well. But you know, the final review is the only thing that I can think of that you would need for the final review is, well, yeah, you're going to look at the quizzes 1, 2, and 3. The final looks like quizzes 1, 2, and 3 merged together. Just questions of those types, plus a question on sorting. So you have to produce the sort code or algorithm or pseudocode on the final. So you need to produce a binary search algorithm on the final and quiz 3. And in addition, on the final, you also need to produce the code for, or algorithm for sorting. So the review would be, you know, going over quizzes 1, 2, and 3, which also going over assignments 1, 2, 3, and 4. So all of those questions on those quizzes and assignments are very similar to what will appear on the final. And, you know, you'll need to practice, like for instance, the questions about classes and objects, like the school bus problem. And the other ones, I think the number, we used a number class. So you'll need to practice that again and prepare for the final with that. But quiz 3 will not have any questions on defining classes. So quiz 3 will not look at all like quiz 2. Quiz 3 is just these functions, these linear algorithms, plus the binary searching. But for the final, you're going to need to get out quiz 2 and assignments for that and review that. Any requests? Do you want me to jump into sorting? I don't know if I could finish it now, but I could start it. Or do you want to wait? Because you don't need to know sorting for the quiz. Wait? How many people want to do it right now? How many people want to wait? Ay, ay, ay. That's a tie. I guess I got to break the tie. How about this? Let's go, let me talk about it for 10 minutes and then we'll break early. And I'll just get the stage set for solving the problem of sorting, okay? How does that sound? Yeah.
Well, we're going to go over sorting on Wednesday.
Yeah, but you know, it's kind of a long topic and it takes a while to get the thing written out and understood.
As far as quiz 3, this is the only material.
Yeah. This is all you need for quiz 3.
So does that
You know-
have time what you do on Wednesday?
What's that?
According to the schedule lab 9 is due on Wednesday.
Oh, lab 9 is due on Wednesday, and that is on sorting, right? Oh, we better do that then. All right, so let's jump into lab 9. So I wasn't thank you. I wasn't thinking about that. Let's take a look at it and just get started on it. Find anything here. Let's see. It must be in 2. I don't have a main function. Let me just do this. All right, let's look at sorting, and somehow don't have a good network connection here. Let's take a look at how this is going to work. So we've got a main function here, and we're going to create a vector of int called v, and then we'll push back a bunch of values onto the vector, and then we'll sort them. So maybe we have say 4 values. Then we'll call this sort routine. And then we'll verify that everything is sorted. So v of 0 should have 1, and so on. It's our test first approach here. Oops. So the vector at this point, the vector v looks like this: 4, 3, 9, and 1. And at this point, the vector will be sorted. So it'll be 1, 3, 4, and 9. So here's the test code. So we'll need to implement that sort function, and it's a void, doesn't return a value. You know what, I'm going to call it sort is kind of a common name. Maybe it conflicts with the name called sort that's in one of the header files that we need to import. So my sort takes a vector of int. It will be a reference of v. Notice we don't declare it as const because we're going to modify v. We're rearranging the values in v. So we'll do something like this. What we need to do is, we have to figure out how to rearrange the items. And let's do it like this. Let's start in the first slot, and then find the smallest value and put it in the first slot. So if we start with this, Let's talk about the algorithm first. Let's suppose we start with this. And what we'll do here is determine that this, we'll have an index, I call it, say, I, and we'll set I here. We'll have another index j, and j will end up stopping or pointing to the smallest value, starting from I going to the end of the vector. And then at that point, what we can do is then swap these values. Oops. And then we'll increment I so that it points to the next slot. So I is starting in the first position. It's scanning to the end of the vector. And from the starting point I, we look to the right and find the index of the smallest value, and then swap it with the value at I. This is, by the way, this is one way. By the way, this is an inefficient sorting algorithm. It has time complexity. I didn't define that term yet. It has the time it takes for this algorithm that I'm showing you right now, the time it takes for this algorithm to terminate is proportional to the square of the number of elements in the vector. And that's expensive because actually there are sorting algorithms which run much faster. The good sorting algorithms will terminate in time which is proportional to the number of elements in the vector times the log of the number of elements. And that turns out to be a lot faster than the square of the number of elements. And let's continue with this. So we start with I now in slot 1, or the second slot. And we range across the whole vector. And we determine that, oh, well, what's at I is the smallest. So we don't have to do anything here. So we leave it alone. Oops. So now let's move I to the next spot. And now we range j through the rest of the vector, and we find that j hits the 4. So we need to swap the 9 and the 4. And I would then be placed at the 9. But actually, we don't need to do this because there's nothing after the last value to swap with. So we don't even get to this point. So at this point, we're in fact we're done. So I never reaches the last index. It stops at 1 before the last index with this particular algorithm. Let's take a look at how to code this up now. So once again, we have I, and we start at 0, and I is going to go to v.size minus 1. We're going to increment I. This is the standard way to write this. We start at 0, and we're less than v.size minus 1. That means the last value of I is v.size minus 2. The last value of I is 2. That's the third slot. Third slot is slot with ID 2, slot with index 2. This is slot 0, slot 1, slot 2, slot 3. V.size is 4. V.size minus 1 is 3. I is strictly less than 3. That means the highest that I gets is 2 in this test code. All right. Let's see what now that we've set I What we want to do is let j range across the values starting at I to the last value in the vector. So that's another for loop. J starts at I. We don't, because everything before I has been sorted. That's the idea. We started in the first slot, and we go to the next slot progressively, one after another, and then at any point in the algorithm, wherever I is, we know that everything before I is already in sorted order, and smaller than everything greater than I. So j needs to be less than v dot size. We need to increment j. Now j needs to hit the last index. J needs to reach the last index in the vector, but unlike I. And so, for each value that we look at, we want to know, we have to, actually what we need to do here, I called that j, didn't I? I'll leave it like that. This is not how I'm using j. I'm going to change this to k. K is the index that, k is the value that points to the index that's the next smallest value. And then j is the index that we range from I to the last element looking for k. Sorry about that. Let's put that in like this. So we have integer k, and we'll set k to I. Actually, we don't need to start at I anymore, because we looked at k as we don't have to compare the value at k with itself, so we can start at I plus 1. Now, if v of j is less than v of k, that means we found a new smaller value. So we're going to have to set k to that index. So k equals j. I'm going fast now. And then when we're done this loop, we want to swap what's at I with what's at k. Let's get the temporary value. We'll take what's in position I. Let's put it in our temporary storage container, and set v of I to v of k, and then set v of k to temp. So we need that intermediate variable to hold to one of the values while we overwrite it. So we're swapping what's at I with what's at k, so we're using temp as an intermediate value. Okay. That's it. Should work. And let's do using namespace.
What?
Using namespace. Hold on there. I'm getting there. Hold on to that. Oh, in there. Right. Right. I need that stuff. But actually, you know what? I think the compiler just takes this. Let's see if we can get away with that, okay? And but I need this using namespace std. Not every compiler will accept this main, okay? And I don't know if this one will. Let's try it. Oh, must return an int. So it takes it without those arguments. It works. Well, it works with that simple test code. Well, we would need to expand the test and make it more complicated. But what I wanted to do is show you the the essence of sorting. And this, like I said, this is one way to do it. There's many different tricks that you can use for sorting, and this is an inefficient sort. And we will not look at efficient sorts; they're much more complicated. But this is the beginning of understanding how to do this sort of thing. Now, it takes time to think about this. Now, I've got 3 variables in here: I, j, and k. What are the roles of those variables? You do have to think about it on your own. And rather than just copy my code and memorize it, I would recommend that you think this over and come up with your own sorting routine. It doesn't have to be this one. But when you do that, make sure that you have sufficient test code. You should have more tests than what I have. 4 elements is not enough, and they should have different kinds of arrangements and stresses. For instance, you should have vectors that have duplicates in them to make sure that works correctly, and so on. Okay, that's it.